This is the third video in a series of videos covering chemical bonds for my honors chemistry class, and this one's going to focus on covalent bonds. Previously we've talked about ionic bonds. So what force holds together molecules this time? Because when we're talking about covalent bonds, we're talking about molecules. And once again, just like all of my other bonds, it is the electrostatic charge attraction. But the question comes into play, well, what are the opposites this time? And to get a sense of what those opposites are, we need to take a look at a molecule. So I'll make a simple molecule here. Let's say I make a H2 molecule. So I have my hydrogen, and it has its one valence electron. And I have another hydrogen, and it has its one valence electron. Well, this pair of hydrogens are going to share, is what we call it, but it's really a tug of war, but they're going to share that pair of electrons there. And let's get a sense of how this works and what the opposites are actually between. So I'll draw this here as a plus and a plus for the nuclei of those two hydrogen atoms. They're each one proton positive nuclei. And then this will represent my shared pair of electrons. So we'll say that this electron is maybe from the hydrogen on the left, and this electron is from the hydrogen on the right. So the actual electrostatic charges, nuclei attracted to not just its original electron, but the electron from the other atom as well. So the specific plus and minus, once again, it is between the nucleus of those neutral atoms and the shared pair of electrons. Opposites attract. One more time, and it's important to realize this. The covalent bond, the electrostatic charge attraction, is between the nucleus and the shared pair of electrons. Alright, so coming back here, looking at my slide, that when we look at the definition of a molecule, that it is a neutral group of atoms joined by covalent bonds. And the key aspect here is that we are talking about atoms. These are not ions this time, it's atoms. And why do we not apply that term molecule to ionic compounds? And molecules don't apply to ionic compounds because you don't have individual pieces of the ionic compound. It relies upon that larger three-dimensional structure. But I can have an individual piece of a covalent compound, and I call those individual pieces molecules. Alright, so one concept we need to address is the concept of diatomic molecules. And many of the elements we find in nature occur as molecules rather than individual atoms. So there are 7 diatomics that we need to be aware of. And we can find these diatomics just by looking at the periodic table. Conveniently enough, they form the number 7. So if you grab a periodic table and you start at nitrogen and you go over nitrogen, oxygen, fluorine, chlorine, bromine, iodine. See, it looks like a number 7 on the table. You might have realized, all right, that's just 6 different elements, so hydrogen is included as well. So our 7 diatomics, one more time, are nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. What does that actually mean to be diatomic? That means that in their natural state, at standard temperature and pressure, that one of these will bond with another one. You will not ever have, for example, a single fluorine atom, that all fluorines will grab another fluorine and they'll form F2. You won't have a single nitrogen atom. All nitrogens will grab another one and they'll form N2 rather than just N. Does that mean that we could never have Cl by itself? And yes and no. That we'll never have just a container at standard temperature and pressure of just plain old Cl. But I can have one Cl if I'm in a compound. So I'll never have just Cl in a container, but you can have Cl with an Na. And you guys all know, well, there's some table salt. So we can have just one chlorine as long as it's in a compound. But this will never be by itself like that. It will always be Cl2, hence the diatomic. If we go back to looking at my slide, you notice that I said, well, maybe there's just 5 here rather than 7. and just 5 because bromine and iodine are actually liquids and solids at room temperature. So the diatomic nature of bromine and iodine only comes into play when they're gases. So something to keep in mind. Another thing to note is that sulfur tends to occur as an allotrope of S8, and phosphorus is P4 as well. So in its natural state, phosphorus is not diatomic, it's, if you want to call it, tetraatomic. There's always going to be 4 of them. In sulfur, there'll be 8 of them. Brings up this concept of allotropes, and allotropes are just different forms of an element where we have different arrangements of the atoms there. For example, here's some diamond, and there's our macroscopic view of diamond, and here's my atomic structure of diamond. But we could also arrange carbon as graphite here, and you see that this is also carbon atoms, and it's just a different allotrope of carbon, a different arrangement of those atoms. Alright, so if a T-Rex were released in New York City, how many humans per day would it need to consume to get its needed calorie intake? And this is number 78 from XKCD's What If. Important thing to keep in mind for your test. Okay, the Octet Rule. The Octet Rule, as we mentioned before, is really just a suggestion. And when we apply it to molecules, it's the same exact concept, where the goal, the want, if we're going to personify our atoms here, the goal is to get to 8 valence electrons, to get to the number in a noble gas. But this time, to achieve a noble gas configuration, that atoms are going to share electrons. An important aspect of this sharing is that we need to realize that it is not a friendly skipping through a field of tulips, holding hands, sitting around a campfire cross-legged, singing Kumbaya, maybe having a little drum circle. It's not that kind of sharing. The sharing here is a desperate tug of war, and that tug of war is going to bring atoms together, and it leads to the overlap of atomic orbitals, thus creating molecular orbitals. An example here would be something that forms a molecule, and a diatomic molecule that we just saw. Let's say fluorine to fluorine bond. And we know fluorine is the strongest element on the table. So each one of these has a very high electronegativity. Their electronegativity value is right about 4 as well. And what that means is that when this fluorine over here runs into this fluorine over here, each one of those are going to violently pull at the other element's valence electrons. So why can't this fluorine steal from the other one? Well, because this one's no pushover. It's very strong. It's going to hold on to its electrons. So this fluorine is going to pull and pull and pull and pull and pull while the other one's doing the same thing. And what we get is a covalent bond. It's a sharing of electrons. Now that sharing doesn't always have to be even, and we'll look later on in this chapter how that sharing is not necessarily even. But just to look back at our last section's material with our ionic bonds. Let's say we had that same really strong element, fluorine, and this time we're going to pair it with something like sodium. What do I know about sodium's electronegativity value? Well, it's much, much, much lower. Sodium is, in comparison, a very weak atom. It's a metal. I see it all the way on the left side of the periodic table in group 1, and sodium is very weak. And fluorine is as strong as you can get. So down here in this earlier example, when fluorine pulls on another fluorine, they share. They're the same strength. But up here, when fluorine pulls at something like sodium, then you don't get a sharing of electrons anymore. Here, sodium is going to lose its electron to fluorine because there's such a vast difference in strength. And we'll look at all of the spectrum between there, where sometimes it's sharing still, but uneven sharing, and sometimes it's such a difference in strength that we get this stealing. All right, so as I look at the boiling and melting points of molecules, what am I talking about here? All right, so let's step back for a moment and remember what happens when we boil or melt an ionic compound. And in that case, it is the ionic bonds that are weakened or broken. And specifically, they're weakened when we're melting and completely broken when we boil an ionic compound. So a high melting or boiling point for ionic compounds are an indication of the strength of that ionic bond. So if I have an ionic bond that's really strong, then I know, okay, it's going to have a really high melting and boiling point. So my equation here, my Coulomb's law to explain the mathematical relationship here, is that the strength of that force of attraction between the ions of the ionic compound, just to remind you that it's proportional to a constant and then my different charges here, which I'll call Q1 and Q2, over my radius squared. So what this is telling me is that the strength of that ionic attraction gets stronger as I have larger charges. So if I go from a sodium ion with +1 to a magnesium ion with +2 to aluminum ion with +3, I'm going to get a higher and higher force as I got a higher and higher charges. And then it's also inversely proportional to the square of the radius. So as I get larger and larger ions, then I'm going to get a weaker and weaker force. So the bigger this radius squared, the larger the ions involved, the weaker the force. All right, so let's compare the melting and boiling of molecules, or of ionic compounds, to the melting and boiling of molecules. So what happens when we melt or boil them? Here, covalent bonds are not broken. Only intermolecular bonds are altered. And that's an awfully good thing. Could you imagine breaking covalent bonds when we, for example, boil water on our stove at home? If we boiled water on our stove at home and broke covalent bonds, we'd end up with hydrogen and oxygen gas and probably blow up our house every time we wanted to make pasta. Not the type of thing you want to happen. The only thing we're affecting there are intermolecular bonds. When you boil water, you still have water when you're finished. You just disrupted the interactions between the water molecules. So because we're not breaking covalent bonds and certainly not breaking ionic bonds, then molecules tend to have relatively low melting and boiling points. All right, here's just some general information on ways to represent molecules. We could have NH3, and that's just my simple molecular formula. It shows me the number and kinds of atoms. Ball and stick model, which we'll use quite often during class, and this shows me a nice three-dimensional representation. It's easy to see those bonds, but the bond lengths themselves are vastly distorted in the ball and stick model. You get a better sense of how close the atoms actually are with a space-filling model. But the space-filling model can be a little tougher to get a good sense of the bond angles. The Lewis structure is something that we'll be using quite a bit as well, and the Lewis structure shows me the general skeletal arrangement of the atoms, and it'll show me lone pairs that are present as well. Perspective drawing we won't see a lot in this class, but a perspective drawing is fairly similar to a Lewis structure, but it makes an attempt to show the three-dimensional nature without having to be a skilled artist to draw something like the ball and stick model. And we use a wedge like this to show that, all right, we're coming into the plane or out of the plane. So the solid wedge here would be coming out of the piece of paper, or the dashed wedge would be show that it's going away from the piece of paper. All right, so Lewis structures were something that we worked on during a podal activity during class, and we started off class with a little bit of practice here for drawing some Lewis structures. And here I have a list of all of my diatomics with the exception of hydrogen, and we were to draw the Lewis structures of them. Some of you guys are a little more savvy in chemistry might be thinking, all right, well, what about O2? Should I draw that as a diradical? But for in class, we didn't actually discuss the diradical nature of oxygen, and we just assumed that it has a simple double bond. It does have a second order bond order anyway, so it's not a bad assumption, at least for our purposes at this level. All right, so looking at nitrogen, I'll work through the full process for nitrogen, and then I'll just show the rest of these structures. So N2, my first step is always to count the total number of valence electrons. So each nitrogen has 5, so I have 10 electrons available. I'm going to connect my nitrogens, and if I only have 10 electrons available, the only way I can do that is through making a triple bond. So there's my N2 with a triple bond, and you notice that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons. All right, if I want to make O2, O2 has 12 electrons, and it's going to have oxygen, oxygen, double bond, and a couple lone pairs on each oxygen. And then my fluorine is going to have a single bond and a total of 14 valence electrons. And you'll notice that Br2, I even skipped Cl2, and I2 are all single bonds as well, and I can draw the dots in. So everything in group 17 is going to have a single bond Lewis structure. So if I ask you on a test, for example, what diatomic molecule contains a triple bond? N2. All right, so we can have multiple bonds that we just saw in those Lewis structures, and in a very simple form, and we'll get into more detail later, but a single bond is the sharing of one pair of electrons, double bond is 2 pairs, 4 electrons, and triple bond is 3 pairs or 6 electrons. How does this influence the bond energy and length? That the bond energy, the bond dissociation energy, increases as we go from a single to a double to a triple. So a triple bond has the highest bond dissociation energy, and a triple bond also has the shortest length. We'll talk a little bit more about what that means and why that happens as we look at the exact sigma and pi bonds that constitute these coming up. All right, so bond dissociation energy, dissociate, that you don't stop associated with something. So if we apply that to bond energy, then it is the energy required to break a bond. In this case, we'll be looking specifically at covalent bonds. So the general relationship with reactivity. A higher bond dissociation energy tends to indicate lower reactivity because more energy is required to initiate the reaction. And we said in a very general sense, all a chemical reaction is we're breaking up some bonds, maybe we're mixing them up and reforming some bonds. So if we need to break up bonds to start a chemical reaction, a bond that has a high dissociation energy means that it will take a lot of energy to break that up to start the reaction. Therefore, it's going to have a much lower reactivity. And my relationship to bond order. Higher bond orders tend to have higher bond dissociation energies. So a third order bond, which is a triple bond, has a very high bond dissociation energy. And we'll see why, because we're breaking both a sigma and 2 pi bonds as we try to break that triple bond. All right, so here we're going to draw some more Lewis structures, a little extra practice. We'll start with CO2. Remember, my first step is to add up my total valence electrons. So I have 4 from the carbon and 6 from each oxygen, and I have 2 of them. So I have a total of 16 valence electrons. My next step will be to draw the simple skeletal structure with my carbon connected to 2 oxygens. And now I'm going to try to satisfy the octet of each of my non-central oxygen atoms. So to satisfy that octet, I'm going to give each of those 6 more electrons. And 6 because the bond already accounts for 2. So this oxygen has 2 here, 3, 4, 5, 6, 7, 8. All right, so now I satisfied the octet of both oxygens, and I used a total of 2, 4, 6, 8, 10, 12, 14, 16 electrons. That means I have no more electrons available to give. I've used all of them that I have. The only problem right now is that carbon only has 4 valence electrons. Its octet is not satisfied. If I had more electrons to give, then I would give carbon those electrons. Why can I not do that? I only had 16 available here, so I can't go about giving carbon any more electrons. So, not letting me erase those. There we go. So what I'm going to do instead is I'm going to have to use electrons that are already in my structure. So for example, I'll take this pair of electrons right here and make a double bond out of it. So I don't remove them from the oxygen. I'm now sharing them between that carbon and oxygen. And I'll do the same over here. Take another pair of electrons from that CO2. So I'll redraw my structure to make the whole thing look nice and neat. I end up with carbon, double bonded, 2 oxygens on either side. And there's my CO2 Lewis structure. Notice that I tried to spread out my lone pairs of electrons that I want, for example, the 3 lone pairs around this oxygen, 1, 2, 3 lone pairs, to try to orient themselves in space as far away from each other as possible. And this ends up being a 120-degree bond angle here. So it's not actually a bond angle in this case because it's just lone pairs, but it's a good habit to get into, and it makes us think about that separation of electron groups, which will be helpful when we talk about the valence shell electron pair repulsion theory. All right, so give myself some room, and I'll draw my O3 Lewis structure. I won't go through quite the same level of detail, but I have 18 electrons, and I'm left with oxygen, a double bond, and a single bond. And let's make sure that I satisfy the fact that I have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. And this guy has its octet, octet, and octet. So it satisfied those criteria. Was there a good reason that I put the double bond on the right? No, absolutely not. I could have put it on the left. And we'll see that it actually doesn't have any double bonds very soon. All right, next up with my CO3 2 minus, that I have 24 electrons available. So I'll make my oxygen and my carbons. And that is completely backwards, and I have no idea what I was doing starting that. Let's delete that guy. So I have, take 2, my carbon connected to 3 oxygens. And I'm going to have a double bond to one of those oxygens. And because it's an ion, I'll put brackets there and the charge of -2 outside. Okay, so looking at ozone, the O3 that we just drew, which of these is correct? And the answer here is neither. Neither of them is actually right. Ozone does not have any double bonds or single bonds. If it did, here's what I would expect experimentally. I would expect that if I got the world's tiniest ruler and measured this bond and measured that bond, that my single bond would be shorter, my double bond would be larger. I would expect it to have 2 different bond association energies and 2 different bond lengths. But it turns out that if I call this bond 1 and that bond 2, that bond 1 and bond 2 are exactly the same. And what accounts for this? And that's the concept of resonance. That it ends up that each of these bonds is somewhere of a blend between a double and a single bond. That those electrons are shared between all 3 of these oxygens. So it ends up being a blending between a double and a single. The word resonance is actually a little bit misleading. That it used to be thought that the bond would flip back and forth from a double bond to a single bond and a double bond to a single bond, and it would resonate back and forth, back and forth, back and forth. And we've since figured out as a scientific community, well, that's not quite how it's behaving. That it doesn't ever flip to a double or to a single, that it's always this blend between a double and a single. And this is how we draw it, the way that you see pictured here, with a double-headed arrow, and we draw, all right, the double bond in one spot, the double bond in another spot, and I draw all of those possibilities. I'm drawing all of the resonance structures. And you might be wondering, well, why do we end up doing that? And it's really a matter of ease, that it could be difficult to try to represent a bond and a half. Like, how should we standardize drawing it? Let's say I wanted to draw my ozone with bond and a halves there. Like, should I make a dashed line? Well, what if it was a bond and a third, which we see sometimes? Like, how many dashes should I do? And there's not a set way to go about doing it. It's not a good set of systems you could use. So instead of doing something like this, Instead, we do something like this, where we just draw all of the possible structures and connect them with a double-headed arrow. I mean, there are some exceptions to that, like some particularly famous molecules sort of get some exceptions to the rule here. If we look at something like benzene, which is a famous case of resonance structures alternating double single bonds, that it alternates between carbon double and single bonds in a ring, six-membered ring. But instead of showing alternating double and single bonds, that we often show that by drawing a circle through there to show that, all right, well, all of these bonds around here are actually the same. Not too pertinent for our class, but just wanted to give you a little heads up about that. All right, so we drew a couple more Lewis structures in class. I'm not going to draw them right now, but we noticed something a little different about all of these. NO2, the first thing we're really going to notice about that is that we get an odd number of valence electrons. So we get 5 for my nitrogen, plus 6 times 2. So I get 17 valence electrons. There is no way to draw that without violating the octet rule, hence my first violation of the octet rule. An odd number of valence electrons, you're going to have to. The next one, SF6. Here we're trying to put 6 things around a central atom. And this does occur. Sulfur hexafluoride, it's a fun compound actually. Look it up on YouTube and watch some videos of what happens to your voice when you drink in a little bit of sulfur hexafluoride. But we can actually draw the structure, and here I have my sulfur surrounded by my 6 fluorides, fluorines I should say. And each one of those will have 6 electrons around it as well. So what clued me in right away that, well, that's going to be an exception to the octet rule? I just have too many valence electrons. That more than 8 are going to be around my central atom. And then a third exception occurs here with boron in particular. And it occurs with boron and other weak, fairly electropositive elements. So boron grouping up with fluorine. We might think that a double bond would form between that boron and the fluorine, but it ends up that that's just not going to happen. Well, let's show as an example here that if I have, oops, give myself a fresh slate. In order to form a double bond, one of these fluorine atoms would have to donate a whole pair of electrons to the boron, forming a coordinate covalent bond. And you know what? Fluorine is just way too electronegative to allow that to happen. And it will not happen. Instead, this is the structure we get. It violates the octet rule because boron only has 6 valence electrons. It doesn't mean the structure does not happen, it just means that when it does happen, we're violating the octet rule. All right, next up with covalent bonding is my VSEPR theory, standing for valence shell electron pair repulsion. And in a very general sense, this means that pairs of valence electrons want to be as far away from each other as possible. The groups of negative electrons will repel. And when we're doing our VSEPR theory, we need to consider both bonds and lone pairs. The bond order doesn't matter. They're all one electron region. So if I have a double bond, I think of it as one electron region. A triple bond, one electron region, which is the concept of steric number here. And the steric number is the total number of electron regions around the central atom. It equals the number of bonded atoms plus lone pairs. And if we try to get a sense of the effect of lone pairs, if I have CH4, methane, it has no lone pairs, it's a tetrahedral shape with a bond angle of about 109.5. Ozone, we have one lone pair, so we're shifting our bond angle from 120 to about 116.8 degrees. And water, 2 lone pairs. Steric number of 4, so it's based off of a tetrahedron, and has a bond angle of 104.5. So it shifted down from 109.5 to about 104.5. So what role do lone pairs have on bond angles? They are going to decrease your bond angle. And why? Well, why? Because they take up more physical space. They're not attracted to another atom. They're not involved in that molecular bond. So they're free to roam about a little bit more and take up a little bit more space. If they're taking up more space, they're pushing down on that bond region. Now in our class, we spent quite a bit of time during class doing practice problems using Vesper, looking at the steric number, predicting the geometry, predicting the bond angle. Spend very much time, we're not going to spend any more time with this video doing that. You should look to the practice problems we did during class. All right, hybridization. So if I'm going to draw out the Lewis structure of CH4, it's a fairly straightforward Lewis structure. I've got my carbon and attached to 4 hydrogens. So clearly, carbon's forming 4 bonds. All right, well, let's look at the orbital notation for carbon. Carbon has the 1s orbital with 2 electrons in it, 2s orbital with 2 electrons, and 2p orbital with 2 electrons in that as well. So the question is how does carbon end up forming these 4 bonds when each of these bonds is sharing a pair of electrons? How is it doing that sharing? Where is the sharing coming from? It looks to me like we have a spot right here and a spot right here. Before I jump to that slide, just take a simple look at maybe a second energy level. For carbon, I had 1s, 2s, and 2p. The very simplest idea of hybridization here is that I have 1, 2, 3, 4 orbitals in the second energy level. Those 4 orbitals can be combined and hybridized in several different ways. I can take the s and the p and blend all 4 of them together to make sp3 hybridized orbitals. And I can even think about this as S1 if I want. So 1s, 3 p's, I'm going to have 4 sp3 hybridized orbitals. It's one way I could arrange them. I could instead take my 1s and take 2 of those p's. And here there will be 3 of those hybrid orbitals. Or I could take my s and 1 of the p's and get 2 of those hybrid orbitals. Because s1 plus p1, just 1s and 1p, I'm only going to have 2 orbitals. All right, we need to look back to where I started. I started with 4 orbitals, so I need to end with 4 orbitals as well. I have to have room for my 8 electrons. So left over to the sp2 is going to be another p orbital. And to the sp, there's going to be 2 leftover p orbitals. So we always end up with 4 orbitals. 3 possible hybridizations for carbon. One is sp3, where I have 4 hybridized orbitals. The second is sp2, where I have 3 hybridized orbitals and 1 original p. And my third is sp, where I have 2 hybridized orbitals and 2 original p orbitals. All right, so I can look at that here with sp3 hybridization. It's the 1s and the 3 p's, giving me my 4 sp3s, and this is how the actual 3D geometry will look. that it is tetrahedral. With sp3 hybridization, I'm going to form all sigma bonds. And here's my symbol for a sigma bond. A sigma bond is a molecular orbital formed by the overlap of orbitals symmetric with the axis connecting the nuclei. So in the specific case of sp3 hybridized carbons, these sigma bonds are formed by the overlap of the sp3 hybridized orbitals. Because they're only connected at one point, they're able to rotate freely along their axis. And they are a decently strong bond because we have a very good overlap of orbitals. An sp3 hybridized carbon can form 4 single bonds. So I have a molecule of propane down here as an example. It's a 3-carbon alkane. And I asked some questions about some of these individual carbons. So this carbon right here, what kind of hybridization would it have? And it would be sp3 hybridized. I know that because it's forming 4 single bonds. 1, 2, 3, 4. 4 single sigma bonds. So what type of bond is that? Carbon-carbon bond. And the carbon-carbon bond is a sigma bond. Carbon-hydrogen bonds, they're also sigma bonds. They're single sigma. Single sigma. Think single sigma. So single sigma bonds. Next I ask, how are the carbons hybridized? Well, if it's forming 4 single bonds, then it has to be an sp3 hybridized carbon. And how are the hydrogens hybridized? They're not. The hydrogen to form 1 single bond does not need to form hybrid orbitals. All right, next we'll take a look at some different possibilities with sigma bonds. And first off, I could have just the overlap of some s orbitals. So here I see an s plus an s gives me in line with the axis of the nuclei, overlap sigma bond. This would be something like H2. I could have an s plus a p give me an overlap here to form another sigma bond. Once again, the key is that it's directly in line with the axis, and it's a single bond. Did I say that before? Single sigma, single sigma, single sigma. And I could also have the direct overlap of some p orbitals here. And here would be a p orbital to p orbital overlap, and we get another sigma bond. Now the case that we were looking at earlier, my sp3 hybridized carbon, would be this example right down here. That is another sigma bond formed by the overlap of the sp3 hybridized orbitals. So although not seen here, sigma bonds can also be part of a double or a triple bond, which we'll see very soon. All right, my next hybridization, sp2. sp2, I'm taking my 1s, my 3 p's, same starting ingredients, and I get 3 new hybrid orbitals. They're sp2 hybridized, plus the 1 original p orbital, and I get this trigonal planar geometry. So what kind of bonds can this actually form? Each of these hybridized sp2 orbitals can form a sigma bond. And this p orbital can form a pi bond, which we'll look at in a moment. So p pi, p pi. So pi orbital from my p and sigmas from my sp2s bonds and the sp2 hybridization. It's formed by combining 1s and 2 p orbitals. So carbon now has the following set of valence electron orbitals: 3 sp2 orbitals and 1 p orbital for a total of 4. Same total as before. The sp2 hybridized orbitals can form 3 sigma bonds, and the p orbital can form a pi bond. And this is what a pi bond looks like. Here it's an overlap above and below the axis of the nuclei. And this is the actual molecular orbital, the pi bond that forms. This might look like it's the joining of 4 different orbitals here, but this is the joining of 2 orbitals. Because remember that this one structure here with a lobe above and below the nucleus is 1 p orbital. So this is 1 pi bond. So what about pi bonds? Those bonding electrons are above and below the bond axis. There's not quite as much overlap of electron regions as a sigma bond, so therefore they're typically weaker. Because it's connected at 2 points, remember 1 p orbital has 2 lobes, one above and one below the axis. They do not rotate. And a double bond is going to consist of 1 sigma bond and 1 pi bond. Does not rotate due to the pi bond, and it's stronger than a single sigma bond because it's both a sigma bond and a pi bond together. All right, my last hybridization here, I have my sp hybridization. I have the same starting ingredients as before. I have the 1s and the 3p orbitals. But this time if I'm combining sp, then I just get 2 new hybrid orbitals and 2 original p orbitals. So just like last time, my hybrid orbitals can form my sigma bonds. Single sigma, single sigma. But this time they can be combined with, this is 1 p orbital, which can form a pi bond, and a second p orbital, which can form a second pi bond. So what is my triple bond that's going to be formed here? It is a triple bond that's composed of 2 pi bonds and 1 sigma bond, which leaves my other sigma bond left over to attach on the other side of the carbon atom. So here I see a little bit more detail of that. My sp hybridization is formed by combining the 1s and 1p orbital. So carbon is left with the following set of valence electron orbitals: 2 sp orbitals and 2 p orbitals for a total of 4 orbitals. Just like the other hybridization, same total as before. But here we can form 2 pi bonds, and the 2 p orbitals can form, the hybridized orbitals form the 2 sigma bonds, and the 2 p orbitals form the 2 pi bonds. Which, just to recap, my triple bond is formed from 1 sigma bond due to the overlap of the sp hybridized orbitals, and 2 pi bonds due to the overlap of the 2p. So 1 sigma, 2 pi. Very high bond dissociation energy, rigid. The sigma bonds could rotate, but the pi bonds cannot, so they make it rigid. And a nice short bond length as well. All right, so that's where we're going to stop our discussion today from covalent bonds.